Okay, listen up, because this right here is the exact trap that catches thousands of Cambridge mathematics students every single year. I want you to picture this. You're sitting in the exam hall, the clock is ticking, you open your 0580 past paper, and you see a perfectly flat horizontal line on a graph. The question simply asks you to describe the motion. Now, let me introduce you to two students we see all the time. Let's call them Alex and Sam. Alex looks at this line and completely overloads his answer with raw mathematical facts, listing coordinates, giving me numbers, but he offers absolutely zero physical analysis of what's actually happening. Sam, on the other hand, Sam is rushing against the timer. He completely misses the command word requirements in the question, doesn't even look at the axes, and just scribbles down, "The car is stopped." And guess what? The examiner pulls out the red pen, and both of them lose massive, crucial marks. Why? Because the answer completely depends on the story the axes are telling you. Are you looking at distance, or are you looking at speed? Today, we are going to fix this exact problem, once and for all. Welcome to The Explainer, where we are going to translate abstract math lines into the real-world stories of currencies, speeding cars, and physical movement. I'm your host, and we are going to simplify the complex today. In Cambridge Mathematics, one powerful image, one correctly interpreted line, is literally worth 1,000 words of explanation. By understanding how to decode these visual stories and applying the right strategy, you're not only going to stop losing those silly marks, but you're going to actively show the examiner that you understand the fundamental physics happening right behind the ink on the page. We're going to dive deep into exactly how top-tier students approach these questions. Here is our roadmap for this session. 1. Decoding conversion graphs. 2. Reading distance-time journeys. 3. Rates of change in gradients. 4. Speed time and acceleration. And finally, 5. Calculating the area under the curve. Let's jump right in. Section 1. Decoding conversion graphs. Let's translate those lines. Okay, the core definition here is absolutely crucial. A conversion graph is a linear graph, meaning a straight line. We use it to instantly convert quantities from one unit to another. Think of currencies like pounds to dollars, or temperature scales like Celsius to Fahrenheit. But I really want you to pay close attention to the word approximate here. Conversion graphs are incredible tools for finding quick, visual estimates without needing to pull out a calculator and do manual math every single time. However, the textbook specifically notes that if you know the exact numerical conversion rate, a mathematical calculation will always give you a more accurate answer. The graph is your rapid visual estimation tool. Now, before we continue and look at exactly how to apply our exam strategy to this, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at how this brilliantly illustrates exactly how that visual tool works. We're looking at a graph mapping pounds on the horizontal axis and dollars on the vertical axis. The problem tells us the exchange rate is 1 pound equals $1.60. So 100 pounds is equivalent to $160. By simply drawing a straight line from 0 to that coordinate, 100 on the bottom, 160 on the side, we create a master conversion key. Now, here's where strategy comes in. If the command word in your exam says estimate the dollar value of 30 pounds, you don't use a calculator. Sam would try to calculate it and waste 2 minutes. You just find 30 on the horizontal axis, draw a line straight up to our diagonal graph line, and read directly across to the vertical axis. It lands closer to 50, so we visually estimate it's roughly $48. It's an incredibly powerful way to process data instantly and secure those marks without burning the clock. Section 2. Reading distance-time journeys. We are adding time into the mix. To properly decode these graphs and avoid the careless mistakes that students like Sam make when they rush, you need a framework. Treat these graphs like a narrative. Step 1, always read your horizontal axis first. This is your timeline, the ticking clock of the journey. Step 2, read your vertical axis. This tells you how far away the object has traveled from its starting point. Step 3 is the most important. Interpret the slope of the line as the speed of movement. Every change in the angle of that line represents a distinct physical action. A steeper line, the object is moving faster. A shallower line, they've slowed down. When you write your answers, we recommend using the PEL framework. Point, evidence, explanation, link. Make your point about the movement, provide evidence from the axes, explain what the slope means, and link it back to the question. Let's see this in action. Let's see how this builds a complete story and watch a real transformation. We have the distance in kilometers of a truck from point A at different times. Each small square represents 3 minutes. From A to B, the line slopes upwards. The truck travels 10 kilometers at a constant speed, taking 30 minutes. Now look closely at the segment from B to C. The line is perfectly horizontal. The clock is ticking forward on the bottom axis, but the distance on the vertical axis is stuck at 10 kilometers. Before our strategy, Alex would just write B to C is a flat line at 10. Red pen, 0 marks. Now Alex applies the Peel framework. He rewrites his answer. The truck is completely stationary for 30 minutes, likely for a delivery drop-off. Green checkmark, full marks. From C to D, it slopes up again, but steeper this time. The truck is moving faster, covering 20 kilometers in 30 minutes. From D to E, another flat line, stationary again. Finally, from E to F, the line slopes all the way back down to 0. The truck is driving back to its exact starting point, taking 1 hour and 15 minutes. See how those abstract lines become a real-world story when you actually decode the command words? Section 3, Rates of Change, Calculating Gradients. This brings us to what I like to call the rule of tool. This simple formula is our specific mathematical tool to extract the exact speed of an object directly from the graph. Gradient equals the change in distance divided by the change in time. If a line goes up 15 meters vertically and across 20 seconds horizontally, you literally just divide 15 by 20 to get 0.75 meters per second. In a distance-time graph, the gradient is the speed. Top students structure their answers by explicitly stating this point, providing the evidence from the axes, explaining the division, and linking it back to the required units. If the command word is calculate, they want to see this exact division happening on your paper. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to it. Look at this side-by-side comparison, because this right here is where Cambridge examiners separate the good students from the great ones. On the left, we have a straight line. A straight line means a constant speed. The gradient is the exact same everywhere. But look at the graph on the right. The line is curving upwards. This means the object is accelerating. Its speed is constantly changing. So if an exam asks you to calculate the speed at exactly 15 seconds, you cannot just pick a point. You have to draw a tangent. A tangent is a perfectly straight line that touches the curve at that one specific frozen moment in time. You then calculate the gradient of your drawn tangent to estimate the speed. It requires precision, a steady hand, and a clear head. Section 4. Speed, time, and acceleration. Time to shift our perspectives entirely. Welcome to our interactive workshop. We're going to put 60 seconds on the clock for a visual challenge. I want you to scan this data comparison. This directly answers the riddle I posed at the very beginning of this session. This is where Sam lost his marks. In a distance-time graph, a horizontal line means the object's distance isn't changing. It is stationary, stopped. But in a speed-time graph, the vertical axis measures speed. If the line is flat, horizontal at, say, 20 meters per second, it means the speed is not changing. The car has not stopped. It is cruising at a constant steady speed of 20 meters per second. You must always scan and read the label on your vertical axis before you write down a single word. That is your core trend. For our second challenge, let's find the flaw. Let's look at what the gradient means in this new context of a speed-time graph. If the line is sloping upwards, the speed is increasing over time. The steepness, or gradient, now represents the rate of change of speed. In physics and mathematics, that is called acceleration. Look at this straight upward-sloping line. In 20 seconds on the horizontal axis, the speed on the vertical axis increases from 0 to 20 meters per second. Using our gradient tool, change in vertical divided by change in horizontal, we divide 20 by 20. The acceleration is exactly 1. Now, here is Alex's flawed answer. The acceleration is 1 meter per second. Can you spot the flaw? Where is he losing the mark? The examiner commentary is clear. He missed the correct unit. The rate of change of speed is acceleration, so the unit must be 1 meter per second squared. Don't drop easy marks on units. All right, challenge 3, speed writing. Let's break down the complete visual grammar of speed-time graphs so you have a foolproof system. A positive slope, aiming up and to the right, means acceleration. The vehicle is speeding up. A perfectly horizontal line means constant speed. The vehicle is cruising. And a negative slope, aiming down towards the right, that is negative acceleration, officially known as deceleration. It means the vehicle is hitting the brakes and slowing down. If an exam line drops from 35 meters per second down to 0 over 25 seconds, your gradient calculation will give you a negative number, like negative 1.4. That negative sign is your mathematical proof that the object is slowing down. Your 30-second speed writing task in the exam is to use POL to say, the object is decelerating, point, as shown by the negative gradient of -1.4, evidence, meaning speed is reducing over time, explanation. Section 5, area under the curve, finding total distance. This reveals one of the most beautiful connections in all of kinematics, and it forms the basis of our final system. If you have a speed-time graph, you can find the total distance traveled by simply calculating the area trapped between the graphed line and the horizontal time axis. Why does this actually work? Because distance equals speed multiplied by time, and on a graph, multiplying the vertical axis, which is speed, by the horizontal axis, which is time, is the exact same mathematical operation as finding the area of a shape. It's an absolutely brilliant shortcut. Let's do a quick visual data scan together and execute this system. Draw your attention to the blue rectangle on this graph. We have an object moving at a constant speed of 30 meters per second. We know it's constant for sure because the line is perfectly flat. It maintains this speed for exactly 20 seconds. To find the distance traveled, we just need the area of this blue rectangle, base times height. The base is 20 seconds. The height is 30 meters per second. 20 multiplied by 30 is 600. The units mathematically cancel out to leave us with exactly 600 meters covered. It really is that simple when you step back, don't panic, and just break it down visually. But let's be real. Cambridge exams rarely just give you a simple rectangle. They are going to give you a complex journey like this one right here. Accelerating, then cruising, then decelerating. This brings us to rule number 3 of our final system, the time management matrix. Sam looks at this shape and panics, wasting precious minutes. You don't panic. You use basic geometry. You simply chop the complex area into basic shapes you already know how to calculate. Here, we slice it into one triangle on the left, let's call it triangle A, a rectangle in the middle for B, and another triangle on the right for C. You calculate the area of triangle A using half base times height. You do the exact same for the rectangle and then the last triangle. Then you simply add those 3 numbers together to get your total of 1837.5 meters. You decode the command word, apply the framework, manage your time by breaking the shapes down, and you guarantee yourself top marks. So, as we wrap up, I want to leave you with this final thought. Stop seeing these graphs as just random abstract lines on a page of grid paper. Start seeing them as the real-world stories they truly represent. A delivery truck pausing on its route, a car slamming on its brakes, a currency dramatically shifting in value. If every line tells a physical story, what hidden narrative is waiting in your next set of exam data? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.